Thank you for coming and good afternoon. Deja vu, last time I was here, I was presenting after Sean Hana and I also showed the same map. So back to the same map again, it's part of an ongoing project on the evolution of urban form on the coastal cities of Ionian and Adriatic Sea. And foreground networks during urban evolution, the effect of length and connectivity on state network integration. And back in Istanbul, I was looking at the sort of impact of urban shape, the shape of urbanized territory on various syntactic measures of the state network. And in Stockholm, I was most interested on the effect of various state patterns, how urban growth occurred according to various models. And this time I'm looking at something else. I'm trying to explain the syntactic conditions in the city through the set of a few lines, a minimal set of lines, those with the highest choice values I call here for the network. Now that's an important question because it has to do with, in one hand, with the way to, the degree to which the roads that originally connected the settlement with other cities become the foundation on which the urban growth occurs. And again, we can refer here to the work of Doxiadis or the more recent work of Emanuele Stano and Mark Barthelemy on the region of Milan in northern Italy, and how that sort of set of roads that connected Milan with other cities, Varese and on, became actually the sort of foundation to support the urban growth. And in this case, the city of Bari in the province of Apulia in Italy, you can sort of compare between 1819 and 2006, the degree to which some of these roads do survive and the degree to which some of them have been wiped out and completely modified because of the, in that case, the growth with orthogonal grid patterns that occurred in early 19th century. That question also had to do with the way we understand the two main kind of urban growth models. In one hand, you have crystalline growth, where the cities grows towards the periphery with not major modifications of the core, as opposed to the other model where concurrent with the growth externally, there are major modifications inside through the opening of new roads and new connections and so on. And I'll come back to this question when I discuss some. Also have to do with the way we understand and design, where primarily through interventions at a few roads, we expect to see that sort of catalyzing effect for the entire city, and normally that intervention happens in this kind of subset of roads of the foreground network. Now the term foreground network has been coined in the earlier work of Hillier and his colleagues. Here we have the city of London, analyzed with the least choice between essentiality. It takes this sort of structure of roads that connect the major urban centers in Greater London. And in contrast to this, however, I'm not using the least angle choice, I'm not using the topological choice. And the object of the study is not on a particular city, trying to understand the relationship between this network and the economic activity or the character of urban space in these subcenters. Rather, I'm looking at a larger sample, trying to discover generic properties of urban form that exist in this sample of cities. Now, the term, as it was explained in the first day by Barthelemy, it's a measure of non-centrality in a network. It's able to number of shortest paths from all vertices to other ones, and it was originally brought from Freeman in the studies of social networks, but some early references go back to the work of Leavitt in 1951. So what I have here is the city of Florence in the three historical stages. And what you have here is the between essentiality, topological choice, and the depth map that we're used to see in the map usually we see depth map here. The darkest blue is shown with gray, just to sort of enable to see the foreground network somehow with the colors. So basically everything blue is shown with thinner lines, the rest of colors have been bolded and brought as a foreground. So to be expected, the distribution of the choice is quite skewed. And like the first presentation, we are interested here at the outliers as opposed to this. And the skewness, as you can see, goes up as the city grows. In the case of Blow, it goes from 4.9 and all the way to 12.2, and that's a phenomenon well known, and it's probably best described in the work of these Korean physicists, and one of them is Jeong, who presented here the first day. So it's what's called the load distribution of the scale-free network, where as the city becomes bigger, more and more choice is given to a fewer set of lines. So following from there, I'm now looking at here the 10 colors in a depth map, the sort of 10 quantiles, and as I showed there, this blue has been converted in that previous figure into gray, and I'm removing this altogether, and I'm sort of interested on the leftover, which is this one that I'm calling the foreground network 90, with 90% highest choice values, and I go on and on to produce the slightly smaller subset of foreground network 80 to foreground network 70 and all the way to 60. So back to the city of Lower. So if we can close that curtain. So what we have here is the number of lines in the foreground network standing against the overall number of lines in the network, and as you can see, that is not actually regular property. Yeah? So the city grows, and actually the number of foreground network doesn't grow the same way. And we're looking now at the foreground network 80, so it's a slightly smaller subset of lines. And what's to be mentioned as well is that this subset is not necessarily a contiguous system. It's sometimes, depending on the nature of the city, it will be scattered into islands or discontinuous sets such as this. And foreground network 70 and 60. So the question then is how can we sort of look at the local properties of that foreground network and ask you whether that would explain the global integration of the city. So it has to do with type 1 laws that Taylor termed in his seminal paper, Architecture of the Urban Object, and to some degree I'm making some comments about the top 2 laws of this from society to space. So let's first discuss the sample. So you have seen this map before, but since then I've added more cities. Now we have 62 cities, starting from the sort of southern point of Mediterranean Sea, which is the Mani Peninsula in Peloponnese, going all the way up to Venice and coming down to the southern point of Sicily. There's sort of any city which is larger than 5,000 population is considered in the Italian side. Those that are larger than 2,000 population are taken in the Balkan side, because those tend to pick up the kind of historical cities, especially at the Croatian coast, where a city actually is defined more politically as opposed to the size. And of course, only cities that existed in 1800 are included, not those that sort of grew recently, came out recently. To be mentioned here is that following the fall of Venice, you have the application of Napoleonic planning models brought from the French, where you have the application of grid-oriented state patterns anywhere in Italy, as well as in Greece, where you have the kind of German and French planners that were brought after the Greek Revolution. In contrast, that the grid pattern is not found in cities from Albania all the way up to Italian border, with the exception of 2 small interventions in Pula and Rijeka, used to be Fiume in Italy. The other thing to consider here is that while anywhere from southern Croatia to Italy we have what's called a crystallized growth, where no modifications happened during the city growth, Albania and Greece underwent the fluid growth where in Greece, due to the Ottomanization efforts, you had interventions of movable guards, and in Albania that was the case because of the application of Eastern Bloc Soviet planning models. What I explained here is the historical cartography, the sources for these maps. The first stage is considered between 1800 to 1900, whatever I could find available, with preference given to the first half of the 18th century. And most of the maps come from the military institute in Florence, the State Archive in Rome, State Archive in Trieste, and sort of what's called the Catasto Franceschino, the cadastre of the Francis I of Austria, that covers anywhere from Venice to southern Dalmatia, and that comes from the archives, State Archives in Split, Croatia. The second batch of maps of the World War II come primarily from military maps, English and British and American. And if one are not available, then I've referred to aerial photographs of the military surveillance, German, Italian, and American. And of course, the third stage maps are easily available through Google Earth or the various planning departments of these cities. So I'll try to show now all the cities one by one, and they're shown to scale. And because some of them are quite small, they're hard to read, but I prefer that just for you to sort of appreciate the difference in size. So we start from the city of Koroni in Greece, going up to Mentoni and Pylos, and these are actually the only three cities that, as they grow, part of the city shrinks. So that's the Ottoman neighborhoods and the castle that got abandoned after the Greek Revolution. Going up to Zakynthos, Patras, sorry if I pronounce it wrong, Corinth, Pactus, Adam, Monica, Ragusa, and Corfu. You can see how, actually the other argument I failed to mention is that unlike the work of Strand and Bartolome, where they consider central place systems, the coastal cities are unique because the growth happens asymmetrically, where what used to be sort of the main part of our groundwork network is not necessarily the case, because the city sort of grows asymmetrically and that center sort of lags behind. So that was another thing to consider in coastal cities. Now we're crossing into Albania, surround, lower. These are, by the way, the 90% of our ground network. Montenegro, Kočura, Bar, Steinland. So we can sort of discuss these in a qualitative sort of manner, looking at the distribution of colors, looking at the way they create the geometry, looking at the degree to which they are scattered into islands or they're contiguous, and you have all categories here. But the focus for the work has been mostly on the quantitative side of it, to, as I said, to find ways that this explains the syntactic or both syntactic integration of this city. So we are now up to the crossing into Slovenia, 3 cities in Slovenia, coming to Italy, Muggia, Trieste, Monfalcone, Grado, and Venice. If you can refer to the previous presentation by Sofia, so that's where the choice is, and with the construction of new bridges and the conversion of many canals into streets, the sort of the highest choice values traveled southeast. That's Chioggia, still in the lagoon, going down south, Ancona, Ortona, and Fredonia. No, let me just speed up a bit. So that's Silibori. Again, the argument I made before, how the interventions that happen all over the Italian coast with the Guerra street pattern are major factor in how that foreground is constituted. Monopoli, Brindisi, Otranto, Gallipoli, ideal city of Avola in the southern tip of Sicily. So what I'm doing next, I'm plotting the skewness values of all of these cities compared to the size. And there is, of course, a general trend that as a city becomes bigger, so does the skewness of choice. However, it's not a complete linear relationship. There are quite some variation where many of these are like outliers. This is Venice, and this must be, this is Rijeka, this must be, anyway. So there is quite some variety that, as I said, has to do, in my opinion, with the nature of the state patterns and how the foreground network is constituted. All the correlations shown here are lower than 0.001 significant. So now focusing on the first component here, the size, and trying to understand whether the size might explain the global integration. If I now plot here the size of the network against the size of the foreground network, and it shows a very heteroscedastic distribution, and instead if I compare the log scale, it's much more homoscedastic. Therefore I'm using that correlation to produce a ratio which is this, the log n compared to log n of foreground network compared to the log n of the size of the network, and that's calculated for all the cities, of course, and these are the means organized in 3 historical stages. That shows that as you move from 19th century to World War II to the present day, that ratio basically becomes smaller. Less and less lines are responsible for sort of gluing the city together. And there is, of course, some variation, obviously, since this becomes smaller by definition as I delete more lines. However, in this case, the change from one historical stage to another is much smaller. So, looking whether that ratio then is explained integration, these two plots show that actually it doesn't. It has nothing to do with size, as it's shown from these weak correlations, and I'm not showing the graphs here for the scatter plot, but for the other two foreground networks, the correlation is quite low. It's the highest, by the way, that 80% foreground network is considered. Now let's look at the length. That's the second in our list. And obviously, as you all know, there is no sort of correlation between the mean length and the mean integration of a city, as shown from this low 0.2 correlation. However, if I take just the mean length of the foreground network, that seems to explain far better the integration of the city, where the correlation jumps to 0.55. And if I go further to consider subsamples in this set of cities, where in one side I consider cities that do contain grid patterns, mainly in Italy and Greece, and those without grids, we see that in the case of grids, the correlation is slightly higher, meaning the length in the cities that contain grid patterns does explain integration, but that completely disappears in the cities without grids. And if I consider here another way of splitting the 3 historical stages, we can see that the correlation is much higher for present-day cities. It's pretty good for the early 18th century cities, and it's much lower for the World War II stage. And that has to do with size, is my opinion, because if now consider the lower 62 cities just when it comes to size, now it's quite obvious that this number increases. With the upper 62, the largest cities have this 0.788 correlation, the length explaining the integration. That's sort of these numbers are tabulated here. So the way we read it is that's the overall sample, and these are the 2 subsamples with grid, without grids, 3 historical stages, and 3 batches for small, medium, and large. For each one, I've highlighted where do I find the largest correlation. And I'm concluding that if I just work with the 80% foreground network, I will be okay. So that seems to capture the highest correlations from this. The next step is to check the connectivity. So again, as expected, there is no link between mean connectivity and mean integration for the entire city. For the old sample, that's what the correlation is, 0.33. And that jumps to 0.65 if I just consider the connectivity of the foreground network. I should mention that the connectivity here is measured as the network is embedded in the city, not the connectivity after I consider the skeleton alone. And so this is the sort of overall tabulation where I add now also the connectivity, and that's, of course, we have much higher relations, although it won't be fine for the case of the connectivity. So it's interesting to see how, as I said, the local properties of the foreground network tend to explain the global properties of the way, in this case, the topological the integration. And the question then comes whether this is an obvious kind of finding, where, because the foreground network was sort of constructed by means of checking the lines that have the highest choice value, or whether this is just something that is unique for cities. Now, to answer that question, what I do, I go next and produce a set of 186 theoretical cities where I basically take the cities and I sort of remove the core of all of these cities. I just delete. And that offset distance is, it sort of means that I'm trying to remove an area which is half of the original circle. So this donut, leftover donut, would be half of the area of the circle. And because these urban shapes are always sort of broken up and elongated, what we tend to remove is actually always less than had it been a circle, so to say. Anyway, so these are the distances that's shown for the city of Lower in Albania, and that is the network after I remove the lines and cut also. I should mention that I'm removing those that fall inside and cut whatever this line uses, and that's the foreground network of this theoretical city that doesn't have parts anymore. And I run the same numbers, and I'm just evaluating here the findings, and as is done only for the 80%. So in red is what it used to be the sort of real city, actual city. What we have in gray is the correlations after that core has been removed. And as you can see, consistently, the correlation drops, and that's the percentage of how much it drops, as I compare the actual city with the theoretical one. That leads me to suggest that what I found is not just a sort of theoretical property of networks, it's a unique property of cities that relates to the discussions in Bill Hiller's papers about the centrality and how the foreground network tries to minimize distance there is an outline here, so if I remove Kyoja, it's that the Kyoja 1808 is one line basically connects everything else. So we should read this minus 35% instead of that 11 there. So that's okay. So the other thing that, of course, it needs more thought, but it's a possibility to look at this intelligibility at the scale of cities, so to say, and checking in this case the residuals, so how far these guys are from the regression line. We can talk of cities where the length is a better predictor of integration, or the same for connectivity, and we can start to look at classes of cities or go further into understanding how these are related for subclasses of cities, but that's deserves more work. And that leads into sort of the next step where, as I said, when I'm trying to explain the foreground network, depending on the degree the city grew asymmetrically, as is the case of a coastal city, or centrally, as is the case of cities located inland, what effect that has, to the degree to which the urban territory grew symmetrically or asymmetrically, and to the degree to which urban shape sort of maintain compactness and fragmentation, or whether during growth urban sort of shape really deforms, the argument I made back in Istanbul. And further, if I leave apart the impact of shape and physiography in the discussion, looking now back at the sort of crystallized versus fluid growth, whether they have to do anything with these properties, and further work coming back to discuss whether certain state patterns would have impact on the foreground network over and above the sort of very rough statement I made about those that have grids and those that don't. In the Stockholm paper discussed the main 5 types, but that has not yet sort of happened. So that's all from me. Thank you.
It's very interesting. I start to think of the paper John published recently in Cognitive Critique, where he describes where he's analyzing lots of buildings and showing that at certain sizes they introduce depth minimizing strategies in terms of corridors or halls or so on. So there's a complexity limit at which point it's common to introduce something that reduces depth again.
The minimal set, so
yeah. So I'm curious if you maybe you're sort of looking at that, but I'm curious of, since you said that only for large cities, it's better for large cities, I'm wondering if what you're capturing in this is when the emergent street pattern forms such a recognizable global level that the developments start to act on another scale.
That's a great point. Yeah, absolutely. So as it sort of picks up, that reinforces even further the process, and that's quite interesting. Yeah, it has to sort of consider further, but that's kind of great point.
Mike Batty did an article about rank clocks, where he looked at American cities and their growth over time, and he showed that. That idea that a large city would attract growth was obviously completely wrong when you looked at it historically, because sometimes the large ones became much smaller and got overtaken by ones that previously were smaller than them, and sometimes the reverse, and it just sort of went all over the place. You've got a data set here where I think you could begin to track that for a different region, a much more diverse region of city types. Not quite so many date periods as he had. It'd be worth looking at that and seeing what you could detect, because I think you've actually got possibly you'll be able to detect when these things do grow and when they don't, what the conditions are.
Definitely, yeah. So, well, there are many factors, of course, but it also has to do with discussion that, let's say, Sean Arnold, how he's belong to a part of a network where, I mean, for historical reasons, this coast of Italy has been historically the backside of the Valley River, that Italy was facing, the Kingdom of Naples was facing this way, that was Venice was altogether a different story. So that was the kind of the back of Italy, turning back to the Balkans, and if you look at the map that Sean just showed, this is now the hot spot. This is where the hot lines in Italy are. So it has had a huge growth, all of this region. But again, it's not the biggest cities that became bigger.
Yeah.
Many of them just remained like Georgia. Just now it's the same as it used to be 100 years ago.
Excuse me, I didn't completely understand. You have removed some actual lines which are low between the centrality, right?
Correct.
Yeah. And the between the centrality is based on topological distance. Right?
Correct. It's basically every time you go from one line to another one, and in that travel you encounter another one, you keep on counting.
And the impedance which is counted is.
It's choice. Actually, if you don't no, it's not. This is
just
topological distance. Yeah. So in depth map, you have this what's called a choice.
And the assumption behind is that those which have a low betweenness are not that important.
Exactly. It's a discussion that Joe brings about foreground versus background.
Okay.
So you just take
so
this set.
That's your notion of foreground network.
Correct.
Okay.
Correct. It's based on that.
Ermal, I think your data set is fantastic. The thoroughness with which you picked up the historical and then mapped axially, I mean, it's stunning, yeah? And consistent, because it's one person doing it, is that right?
Correct.
Yeah, okay. Seriously, you should think about making it go open source. Yeah, I think if you gave that data set up to the community and challenged people to investigate and to look at things, you just get so many citations.
Thank you.
You should make it open source. It's fantastic data set.
No other one? Well, thank you.